Hi, today I wanted to go over a basic overview of Big O notation. So, Big O notation is a mathematical way that we can describe the efficiency or what's called the time complexity of a given algorithm. So, basically, how fast does it run? We could also use it to describe how much RAM does it use, but in this case, we're just focused on computation. So basically, it talks about the time complexity or efficiency of an algorithm. So let's go over some common notations from fastest to slowest, and then some extra ones. So we have O at 1 up here. O at 1 is also called constant time because what that means is no matter how big an array is, so we have an array right here. No matter how big that array is, it's gonna run it's gonna run the same amount of operations each time. So this array could be 5 characters long, it could be 1,000,000 characters long, and it's still gonna run the same speed. That's why it's called constant time. This is the fastest time. Next, you have O at n. This is called linear time, and what this means, what the n in here refers to is the size of the array that we're talking about. Or it could just be like the number of yeah, basically size of the array. That's a good way to think about it. So for this right here, string len array this is in C, but what that basically does is that just loops up to n. This is the size of the array, which is basically n in this case. You see how we have a loop that runs n times. It goes from 0 to n. So this loop runs n times. So if the array is 5 characters long, it's going to run 5 times. If it's 1,000,000 long, it's going to run 1,000,000 times. That's why this is called O at n time. Now there's another couple examples of big O notation that I want to describe. So for this one, as you see, we're running up to n over 2. So would this be O at n over 2 time? No. It's still over it's still O of n time because O at n over 2 is the same as 1/2 of n. But in big O notation, we don't care about this constant value right here. If it still runs basically up to like proportional to n in a linear fashion like this, then it's still O at n. And this is another example right here. As you see, from we're running n times here in this for loop, and then we have a second for loop after it. So technically, you could describe this as O at 2n time, but similarly, we don't care about that constant value. So we could just erase it, and it's O at n. So that's O at n time, that's linear time. And now we have O at n squared. We're getting a little bit slower now. This is quadratic time, you can call it. And what that basically looks like in code is while this looked like just one loop, while loop or for loop, in this case it's a for loop, this is two nested loops because this loop right here, if we look at this, again, this right here runs n times. So this loop right here is O at n. However, that's inside of this loop, which is also O at n, because you see how it also runs up to n. Technically n minus 1, but again, we don't care about that constant stuff, so we can just X that out, and it's still O at n time. This is actually a selection sort, which runs at O at n squared time. I got this from Geeks for Geeks, and I just modified it just a little bit. But yeah, so we run this O at n for loop n times. So that means that we have n times n, which is n squared. So that's why this is quadratic time. And then you can also have O at n cube, O at n to the 4, or whatever. What this is basically like, instead of 2 nested loops like this, we have 3 nested loops. And for this, instead of 2 nested loops, we've got 4 nested loops, and so on. It can go up to however tall you want. So that's O at n squared. Now, even slower, we have O at 2 to the n. This is really horrible. This is absolutely horrible. But because think about this, like if we have an array that's, let's say, or we have the iterations, let's say n equals 5. That means we have to run this 2 to the n equals 2 to the 5, which is 32 times. And if n is equal to 10, if we have an array, that's just 10 big? Well, that's 2 to the 10. That's 1,024. And then 2 to the 20, if we have an array of 20, that's this number. That's a lot of iterations. So this example that I gave here, this is the Fibonacci sequence implemented horribly through recursion. But you see how quickly the amount of operations escalates? So that's why we don't want to program an O at 2n. That's really 2 to the n. That's why it's really, really slow. Then, if you thought we couldn't get slower, you're wrong. O at n factorial. Oh, also, this is called exponential time. Exponential time, right up here. Exponential time. Beautiful. But this is factorial time. You can call it. This is the worst runtime, at least what I know. So basically, this if you want to compute the factorial, if the size of an array is 1, then it runs 1 time. If it's 2, it runs 2 times. If it's 3, it runs 6 times. If it's 4, it runs 24 times. If it's 5, it runs 120 times. If it's 6, 720 times. And it just keeps getting worse and worse and worse. I believe 10 factorial is in the millions. So this is the absolute worst time. You're hardly ever going to see this runtime, but it's good to know. Alrighty, now let's get into some different algorithms. So this is O at logn time. O at logn is called logarithmic time. Logarithmic time. And the log is at base 2. Always, because computer is binary. So when you see log in math, it's usually base 10 or base e, but it's base 2 in computer science. So O at logn is faster than O at n, so it's faster than linear time, but it's slower than O at 1. And here's a basic example. So if I have to run n times, let's say for an array or something else, if I have to run n times, then if I have this loop, but every iteration I multiply by 2, that means that I'm basically cutting the amount of the size of how much I have to iterate through in half each iteration. So if I have n equals 1,000, let's say 1,024, then I starts at 0. Oh, actually, this should be a 1. This should be a 1, sorry. So it starts at 1, because 0 multiplied by 2 is just still 0. But it starts at 1, then it goes to 2, then 4, 8, 16, 32, 64, 128, 256, 512, and then we reach 1024. That's only like 10, 11 iterations. That is absolutely incredible. That's very fast. So we went from the size of the array is 1024 in linear time. That would be about 1024 iterations in the worst case. But for O at logn, in the worst case, that's 10. That's incredible. It's still slower than O at 1, because O at 1 is 1 time. But it's faster than O at n. Here's another example. This is binary search. I'm not going to go in too deep about it, but binary search is another popular O at logn time. Because as you see, we end up cutting the amount of stuff in the array that we have to iterate through in half every time. So that's O at logn time. Now another common one is O at n logn. This is in between O at n squared and O at n. So it's faster than O at n squared, but it's slower than O at n. It's still a pretty good runtime, mostly for like sorting. For example, merge sort, heap sort, run at O at n log n time, and quick sort runs on an average of O at n log n time. And there's a bunch of other sorting algorithms that run about that as well. So basically, imagine O at n and a nested O at log n. So this loop right here, like we did, this should be 1 again. Like we saw before, this is O at log n. And as you know, this for loop right up here we run this n times. So n multiplied by log n is equal to n log n. So that's where we get this time complexity from. And again, O at n log n is faster than O at n squared, but slower than O at n. So that's a basic overview. To just go back to the beginning, O at 1 is constant time. O at n is linear time. You know, if an array is 100 long, it's going to iterate around 100 times or some multiple of that other than n. And then O at n squared is quadratic time, like two nested for loops, essentially. O at 2 to the n is exponential time. You're hardly going to see it in application because it's absolutely horrible. O at n factorial is factorial time. Again, you're rarely going to see this too, but it exists. And then log n time, this is common. This is very fast. And then there was O at n log n. And that about covers the big O notation, the different time complexities for big O notation. I hope this video has been helpful for you. I'll also put all of this code on my GitHub repository that's linked in the description. Thank you for watching and have a good day.